Hello, hello. Please, can you hear me? Please, I want to see in the chat session if you can hear me. I want to know. So, if you can hear me, just let me know, please. So, good evening. Welcome to today's stream. EE366 is what we are looking at today. Power electronics. We're looking at power electronics. This is our first stream in this playlist. So, please follow suit. Please let's take 3 minutes. Okay, let's try to get our friends to come on board. Let's take 3 minutes, please. So if you know someone who's supposed to be watching, kindly get them to watch. This stream will last for an hour. As I said, sorry for any inconvenience caused. We are more than an hour late, and I'm very, very sorry. Things came up. Things came up. So yes. Coming to us is very, very inconvenient, so we'll come for it. You like just don't like long things. The activities in the fact that it's just long. God bless you for teaching us. Please, I'm sorry. Okay. When we went for the 3 minutes break, I should have muted myself. I didn't mute myself. So sorry for any sound you heard you weren't supposed to hear. Thank you very much. So let's start. Let's start. So we'll do some today. We'll continue tomorrow, God willing. Right. So what are we looking at today? What are we looking at today? We'll be looking at wire power electronics. That's what we'll start with. Right. Wire power electronics. So then we'll look at the concept of commutation. The concept of commutation. Now, this is a very, very key concept to understand. Understanding this concept, understanding this concept means that units 2 and 3 will go smoothly for us. Okay. And then finally we'll look at power loss calculations. And then God willing, we should be able to get to the thermal problem. So this is where we are supposed to get to. Hold. Please hold on, okay? We are checking something. Right. So so these are the things we'll be looking at today, God willing. Right. So let's talk about why power electronics. Please, this side do a lot of reading, okay? Do You must do a lot of personal reading. Let me go to the slides. Okay. So all this part is about why we are doing power electronics. So you can see. So yes. So please do well to read all this side. Okay. Mhm. So here's the thing. Here's the thing. We have an input. Okay. We have a certain power in a certain input, and then we want to bring this power to the output. Right. So the whole idea of power electronics is that we are studying components that we'll put here that will take this power and give us power at the output with ideally no loss. Ideally, no loss in components. So we want to put a certain component here. We want to put a component here that would ensure that P in is equal to P out. Ideally. Okay. Please follow. We are building up. So now let's see. So they realize that when they put resistor here, when a resistor will cause I squared R losses, right? So the power between the power difference between the input and the output might be intense because of the presence of I squared R losses due to the resistor. So we can't put a resistor in the middle. So we want to put something called power converter in between. We want to put a power converter in between. A power converter is made up of switches and energy storage elements. So we are building up concepts. Oh. So the power converter is made up of switches. So all forms of switches that we know from linear electronics. So we can have BJTs, we can have diodes, we can have MOSFETs, and so on and so forth. And we also have the energy storage elements. Energy storage elements as inductors and capacitors. So these components form up what we call a power or make up what we call a power converter. Okay, now so here's what we want to do. Here's what power electronics is basically about. So we know that power electronics is at the heart of renewables, right? Yes. The advancement in inverters, DC to DC converters, all these devices are power electronic devices. So power electronics is at the heart of renewables, the world wanting to go green, carbon free, electric cars, electric ships, aeroplanes, all these things are power electronic devices. So hence the need to understand how these devices work. Right. So how or why is it that I'm saying that when I use a switch, ideally there will be zero power loss. This is why. So please take note of this. Okay, this is what we're doing. So We all know that this is how a switch looks like. This is a switch in the off state and a switch in the on state. So when the switch is in the off state, no current flows through the switch, and a certain voltage of any magnitude flows through the switch. Like based on the external circuit, some voltage will be across the open circuit voltage. This implies that the power given by IV will be zero. So the off state power loss is zero. Now in the on state, we know that a current flow through, yes, a maximum is an open, it's a closed circuit, so current will flow through, and then some voltage, zero voltage will be set up across it, right? Yes. So there's no resistor to cause a voltage drop, so no voltage drop here. So subsequently, we can say that P is equal to IV is equal to 0 times X is equal to 0. So ideally, in the on and off state, the switch should have zero power loss, and that is why it becomes suitable to be used as this component, as power converter, together with energy storage elements. So ideally, the on and off state of the switch ideally is instantaneous. Like it's when I say on, it goes on. When I say off, it goes off. Right? So we need these storage elements to ensure smooth electrical flow. Smooth. Sorry for the noise in the background. We don't have an ideal room to have this broadcast. So sorry for the noise in the background. Let's move on. So smooth electrical flow. We want to ensure smooth electrical flow. That is why we are using these energy storage elements. Yes. Let me go to unit one slide. Unit one slide. So please take time. Take time to do the reading. I'm coming. Let me see. So yes. So here you read about power electronics. This unit two. Sorry. This unit two. This unit two. I'm coming, please. Um, hold. I'm coming. All right. So unit one slide. Yes, this is what I want. So here, this part talks about why we're reading power electronics. So take time to read. Take time to read all this side. Please take time to read. Okay. So you read. You read. Please read. Do well to read. So here's what we're talking about. Why power electronic circuits will take a certain power from the input, give it to the output, using switches and energy conversion devices, inductors and diodes. So take time to read. Here's why we are using switching. Yes. Yeah. All right. Sure. So this is just some background info. Now let's move on. So we said that what we'll be using switches and energy storage element. We said the switches we have MOSFET, BJT. So please kindly take time to read about these things. How BJTs function, how MOSFET works. We also have the diode and then IGBT. Please take time to read on them. Okay, so switches are classified into three classes. So classes of switches. So we have the first class of switches known as so we have we have the first class of switches known as the controlled devices. Control devices. And these are devices whose on and off states are controlled by some input voltage or input current to their base. Right? So you know that if I have a BJT like this, right, I must have a certain voltage, a certain base voltage supplied here, or a certain base current, right, which will cause this BJT to function, to be in the on or the off state, right? So this means the BJT is a control device. We also have the MOSFET as a control device, and so on and so forth. Second, we have the uncontrolled devices. And an uncontrolled device, we have the diode, right? We know that in the diode, like no external control the diode, no external input control the diode, right? The diode is either on or off, based on how the external circuit around it is functioning, right? Like for example, if the external circuit will allow current to flow through the diode this way, it's on. If it will allow current to flow through this way, it's off. So that means the diode is an uncontrolled device. We have the third class called the latching devices. Okay, with the latching devices, their own state is controlled by some inputs to the gates, and the off state is controlled by the external circuit. So that one is like a light between controlled and uncontrolled devices. So these are the classes of switches that we'll be working with. Okay, don't forget, don't lose track of the concept. We said that we want to take power from input to output through a circuit made up of what? Switches and energy storage. Please don't mind my handwriting. That's what I'm saying. Energy storage elements. If you have any question, ask. Sure. So we've spoken about the switches, right? Now let's talk about the energy storage elements. So we have two energy storage elements, as I said earlier on. We have the inductor and the capacitor. Okay. So the inductor stores energy in the form of current. So it's given by half L times I squared. Capacitor stores its energy in the form of voltage. So it's given by half times CV squared. So keep this in your mind. So which means that if an inductor has current in it, it will want the current to remain in it. It wouldn't want to lose the current. It wants to store the current, right? It's to storing the energy. Same for capacitor. It will want to keep it voltage, right? So let's move on. So now let's talk about an inductor. So this is how an inductor looks like. Just a winding. So inductive current flowing through, some voltage here, has inductance L. I'm coming here. I'm a little bit here. So let's see. Now we said that what the voltage across an inductor is given by L di dt. So let me make di the subject. So di is given by V over L dt, right? Yes. So I want to find I. So I integrate both sides. 1 over L can come out. I have 1 over L integral V over this is a function in terms of V dt, right? When I integrate the I'll get I, right? But then let's say I have a certain voltage function V of t like this. This is a voltage function, a continuous voltage function in a time domain, right? So if I want to find the area under this, It's just me integrating it between two times, right? So the integral from T1 to T2 of the voltage function is giving me the change in current. So this change in current is given by current at the time T2 minus current at the time T1. So this is what I have. Integral from T1 to T2, voltage function dt. So this is a very, very important function to take note of. All right. So here, as I said, my delta I is given by this is given by what? The area under this voltage time curve, right? So it's given by voltage time area divided by the inductance, right? So the area under this voltage time curve is given as the change in current. So here's how we come about it. So this is something very important that we should take note of. Okay. And we say that in the steady state, in the steady state where the current at T2 is equal to the current at T1, then the change becomes zero. So we say that, so this is the first point to know. Then two, the voltage, average voltage across an inductor, the average voltage across an inductor in the steady state is equal to zero. Okay. Yes. So in the steady state, the capacitor will behave as if like for any two times taken, the current between them will be the same. The current at those two times will be the same. You get it? But we see that the inductor is feeling reluctant to change its current. So therefore, we can see that then the average voltage across an inductor in the steady state is given by this difference is zero. This difference being zero means that this will give me zero, right? So that's how yeah. All right, sure, let's move on. So that's it for inductor. So we've seen that for the inductor, the change in current an inductor is given by the voltage time area over the inductance. We will make use of this thing intensely when we get to the unit 3. So kindly pay attention. And then we see that the average voltage across an inductor in the steady state is also zero. Alright. Now let's talk about capacitor. So this is how a capacitor looks like. Parallel plate capacitor, current, voltage with capacitance C. With capacitance C. Right. So here we know that what the current through a capacitor, sorry, is given by C divided dt. So here to let's make V the subject, I get the is equal to 1 over C times I dt. Right? So here, integrate here, I'll be getting change in V is given by 1 over C integral of I dt. And we said this means that the voltage at time T2 minus voltage at time T1 is a change, right? So it's the same as the integral from those two times, time T1 to T2, a certain function of time dt. So here it means that let's say I have a certain function of time, current function of time like this, right? So if I find between these two points T1 and T2, if I find the area under this curve, Area means that was integral. You remember this one. If I find the area under this curve, right, and divide by the capacitance of the capacitor, it will give me the voltage across the capacitor. You get it for any two times, right? The voltage difference for any two times. So here too, I can write this as change in V is given by this. What is the current time area? Is the area under the current time graph? So the current time area divided by capacitance. Another very useful equation that we'll use in the intensity. Now here too, if I say okay, in the steady state, V2 at T is equal to V at T2 is equal to V1 at T1, then I can say that the average current through a capacitor in the steady state will also give me 0. So that's something else to note. That's the second point. The first point is that the average current through capacitor in the steady state is equal to 0. In the steady state is equal to 0. Is equal to 0. So for any periodic function, we know that what the average of it is just what? Is just the area under the curve divided by the period. Okay. So we'll make use of what I said right now later. So let's move on. So these four things we've seen are called the four rules, the four important rules in power electronics. That the change in I is equal to voltage time area over L. Change in C is current time area. Change in V is current time area over C. And that the average voltage across an inductor is equal to 0. And the average current through a capacitor is equal to 0. Sure. Let's move on, please. Let's move on. Now, so now we've spoken about why power electronics. We've done that already. We've also seen the concepts of power electronics, right? Now let's move on to the next thing. Let's talk about commutation. This is by far, I would say, like one of the most important things you must understand in this course. How the energy storage element play a role in commutation. Okay. So let's take an RL load. So I have inductance series with a resistance, right? And then there is an anti-parallel diode here. There's a voltage supply Vs coming from this side, and then let me put a switch here. Let me put a switch here. So this is my diode, this is my L R, this is my switch. Let me call my switch Q. Please, let's get this concept once and for all. Isiama, T is Isiama did a very good job at making us understand it. So I'm just picking up from there. So let's also try to understand it very well from here. So we must know that this is a switch, right? This is a switch. This switch, this Q, it may be a MOSFET, it may be a BJT, it may be a IGBT. It's just a controlled device, a controlled switch. So either of these. So you must, if it's controlled, it means that I can say, oh, then this thing actually looks like this. Actually looks like this, right? Then I'll have, let's say I can have something like this here. Let's say it's a BJT, so I can have it like this. Right? And there's a certain gate, a certain drive here. So this drive is set to for this to operate in the cutoff. We know that anything is off. If it's set to operate in a saturation, means it's on and current is flowing. So, but for now, let me just present it as which it is. It's to make the explanation simpler. Right? If you have any question, do also ask. So this is a switch driven by an external circuit to go on and off. Okay. Now this switch its on and off state is being driven by this graph here. So it is on for this period, it is off for this period, it's on, so it's periodic, it's a periodic control, it's periodic switching. So it's off for this state. On here, off here, on here, off here. Now the ratio of the period for which the switch is on over the entire period is what we call the duty cycle, D. On. Thank you at UC. So this will become duty cycle of the, is on for a certain duty cycle of the period. You get it? So this will be, this is my entire period, right? And then you see that it's on for a certain duty cycle of the period, and it is off. So this duty cycle is expressed over 1 because the entire period is 1. So it can be, let's say, duty cycle 0.6 or 60% is the same thing. So which means that it will be off for 40%. So here is just 1 minus duty cycle of the period. Okay. So this is the waveform that's controlling the switching of this BJT or IGBT or MOSFET, this switch here. MOSFET switch here. Sure. Concept building up. Concept building up. Now let's see what happens. Let's see what's happening here. When when this voltage source is supplying, okay, it will supply only when I close the switch. So when the switch is on, right, when the switch is on, current starts flowing through this branch. So current is coming, current gets here, this diode is reverse bias, this bar is blocking the current, so it's reverse bias. So the current, please hold on. Sure. I'm saying that, sorry, the switch comes on, diode is reverse bias, so current flows through here. So there's current flowing through the inductor and the resistor. So in the inductor, please pay attention, okay. So here I'm in the on state. I'm here, switch is on. Current through the in this load, right? There's current, so it will rise. When we say the inductor, the current just doesn't jump. The current rises, like it transients through the inductor. So therefore, the current rise. Let me explain something first. Come in. Let me explain something first. Using a diagram in the slides. Right. So this is what happens, okay. So now initially, I'm using this simulation to explain. Initially, when the switch comes on, the inductor takes current, right? Yes. So Switch is on, inductive current is on. So current flows through the inductor, flows through the switch, comes back here. So the inductor has built up current. The inductor has built up current. All right. Now, when the switch goes off, when the switch is off now, this part of the circuit is non-conducting. It's an open branch. So no current flows through this branch. But don't forget that we said that what? We said that the inductor is an energy storage element and it stores this energy as current. So the inductor has stored some current, which it will now supply. So initially when the current was flowing this way, we had our minus here, plus and minus here, right? If I have a voltage source like this and I have a resistor like this, if here is part connected to the side is plus, so same. This part is plus connected to the voltage source, fine. Now, when the switch goes off, okay, when the switch goes off and the inductor is now supposed to supply current, it will now act as a source, right? So as a source, look at it to supply from the high terminal, high polarity terminal. So it means now in this case, in the inductor here becomes plus, here becomes minus, so that it can still supply current in the same direction. So that it can still supply current in the same direction, right? So this current now comes down, open circuit, so the current flows through here. So the current now starts flowing through the diode, and the diode now starts conducting. So initially, switch is conducting, current is flowing through switch. Now switch goes off, no current flowing through switch. All the current is flowing through the diode now. So we say that what this is the concept of commutation. Commutation, it has changed, the current has changed over to the elements, right? So the process by which this current flows through the RL and diode by current driven from the inductor is something we call freewheeling. So freewheeling is current flows through the inductor, resistance, and diode driven by current from the inductor. So it makes this diode what we call the freewheeling diode. But without that diode, there wouldn't have been any path for the inductor to supply through, because here would have been open circuited. So it's called the freewheeling diode. Sure. So I'm saying that on state, reverse bias, current flows through here, right? On state, current flows through here. Off state, off state, the inductor will reverse polarities and will now start supplying current through this branch, which will go through the diode. Diode now becomes conducting, right? So now, if I have something like this, the current in the inductor rises up to a certain level, right? In the on state, then in the off state, it will now supply current. Supply current. Now, it doesn't discharge oil current, because don't forget that the inductor is reluctant to change its current, so that it is supplying the current. Then the next on state comes again. The next on state comes, so the inductor current will have to go up again. So the inductor current goes up again. Again. So when it comes on, it means this is now reverse bias. So you go back to the initial process. Then when it goes off, when it goes off, the inductor will now supply current. So this happens until we reach a steady state where now the waveform is like this, is periodic. Like the peak and the trough are the same. So here initially the build up state, like the inductor builds current not to its highest level. Then as it's discharging, it comes on again. So it picks up the current, goes up. Then switch goes off, so it starts discharging, then picks up current again. But you get to a certain steady state. And you get to a certain steady state. And now the charge and discharge is the same. That's what we call the steady state. In our analysis of electronics, we will be dealing with steady state. This is the state that we'll be dealing with. All right, please, I hope it makes sense. So take 30 seconds, let it sink in. Hold, I'm coming. Yes, so this is the concept of commutation. This is the concept of commutation. Okay. So I hope it makes sense. We'll come back to this again in unit 2. So that's unit 1. That's unit 1 recap. So I've explained the simulation here, how initially bills get to a certain steady state. Then now it looks the same. So this is it. We've spoken about this. We've spoken about the commutation, what's actually happening. We've seen these 4 rules already. Yes, we've seen these 4 rules already. We've spoken about in the steady state, the average currents being this, freewheeling. Explain this concept very well into detail. So that's thank you for staying through unit 1. Now let's take a leap of faith into unit 2. Let's take a leap of faith into unit 2. Please, if you have any question, do well to ask. Hello. Right, we are on. So I'm wiping this. Right. So unit 2. Unit 2 is going to talk about. We come to look at the into detail the components, the switches, and how they function. So unit 2. So yes, so as we said, we are using switching devices. Sorry for the noise in the background. We are using these are the classes of switches. This is what we want to do ideally. We've spoken about all this side. So simply read all the side. Kindly take time to read. Because I saw the midterm, we had some reading questions. So this drips and diffusion currents. We have so just read about them. We have gate drivers, base drivers. Kindly read. Then I took diode, how it functions, how BJT functions, how MOSFET functions, and then power losses. This is my concern. So now you see we said that we've established the fact that we want to take a certain input power, right, and give it the output with ideally zero loss in the past. But there is no free lunch, there is no ideal scenario. There definitely are some minimal losses. So we are coming to look at the power losses in the switching devices. Power losses in the switching devices. This is the next concept we are taking. Power losses in the switching devices. All right. Now, there are three types of power losses in switching devices, okay? By virtue of the fact that the switch is on, there is an on state loss. So first we have on state loss. Secondly, we have, you see, you are turning it on and off. So during the transition, we have another loss called the switching loss. So it's called the switching or transition loss. Switching or transition loss. We have the on state or conduction loss. All right. Then finally, we have the off state or blocking loss. When it's blocking, when it's in the off state. So these are the losses that we will be considering. So our BJT, our diode, our IGBT, MOSFETs all have these losses. So we're looking at all these losses in our power converting circuits. All right. So we'll take them one after the other. So we'll take the on state loss. So let us consider the first amongst the losses, the on state loss. Okay. So before we look at the on state loss, let us look at equivalent models. Equivalent models of the switches. Equivalent models of the switches. So how do I model a diode? What's the model of a diode? You know that a diode is modeled as a certain voltage source in series with a certain resistance. So this is, let me call this one vein forward, like forward voltage. This is a series resistance. So this is the model of, please, it's important to know this model. Take note of it. We'll see it used very soon. So take note. Secondly, a MOSFET is modeled as a resistance. So this is a MOSFET. And it's just notation. So R on. A MOSFET is modeled as a resistor. And then transistor or IGBT is modeled as a voltage source. A transistor or an IGBT is modeled as a voltage. So let me call it VCE. VCE. Please kindly take note. So we say that a diode is modeled as this, right? Then a MOSFET is also modeled as this. And then a transistor is modeled as a voltage source. Fantastic. So there you have it. So now we've seen the equivalent models of the switches. Now let's see. Now We know that power is given by VI, right? P is VI, P is VI, P is VI. We know this. So I can say my power is given by a certain voltage source. So let's say if you have a switch here like this, I have a switch here like this. Let's say the voltage here is VAB. It's given by the voltage VAB multiplied by the average current. We said that average current is given by what? If I have current here like this, let's say the average current is just the area under this curve. So that is the area, right? So the area is integral. So I'm talking about this. So this implies that the power is given by VAB multiplied by I average. So this is the on-state loss. This is the on-state loss for an equivalent voltage model. What am I saying? I'm saying that you see we said that what a transistor is modeled as a voltage source like this, right? With voltage VC, which means that the on-state power loss in the transistor is given by the voltage across the transistor times the average current through the transistor. So very soon we'll see how to compute this average current. But just know that if the model is a voltage model, if it's a voltage source model, then you multiply that voltage by the average current. Now let's consider the case. We also know that power is also given by R I squared. Right? Now, if the model is a resistor, then we'll use the RMS current. I RMS squared. So if the model is a voltage source, we use the voltage times the average current. If the model is a resistor, then it's the resistance times the RMS current squared. Now let's see how this relates to the model. That's why I said it was important to know the model. So let's see how it relates. So we know that for a diode, it's modeled as what? A diode is modeled as a voltage source in series with a resistor. So this, let's say vein forward, this is my series resistance. This means that the on state loss, so this is a P on. So this is the device. So you can have this table, this device, this is model. Thank you, Akani. This is on state loss. So because this is made up of a voltage source and a resistor, the on state loss here for the voltage source is what? Times average current. And for the resistor, it is RS times RMS current. So the next thing we'll look at is how to compute the average and RMS current from the waveforms. Okay, beautiful. Now let's take the next. Let's take a MOSFET. Alright. A MOSFET is modeled as a resistor like this. Therefore, the on-state loss of a MOSFET is given by R. Let's eat this R on. Let's say it's given by R on times I RMS squared. Then finally, for a transistor IGBT, let's say IGBT. So for a BJT, so this is bipolar I meant BJT IGBT, which we modeled as a voltage source. Let me call this VAB. Then its on state power loss is VAB. What's the voltage source? We use the average current. You see, so this is how beautiful it is. This is how the models connect to the on state losses. Get it? Because we have two of the power equations. P is equal to IV or P is equal to I squared R. So when do we use which? If you are using IV, make sure your I is average. If you are using I squared R, make sure your I is RMS. Fantastic. Now let us look at our next table. So please let's look at that. So please you can have this table down. Let's look at the next table of importance to us. Is how to find the how to find the average current. Okay. Now let me explain here. Let me draw our diode here. Source here. So we said that we are considering this. We are considering this in the steady state, right? Yes. So we are considering this in the steady state. So in the steady state is when this is the steady state. It's when the current has built up already. Such that now the charge and discharge is at a certain value. It's not at zero again, and it's constant. So in the steady state, during the on, so let me just do some short dashes here. Please follow, okay? And please, it's important to know how to draw the waveforms very well. Because if you know how to draw it, then now the course becomes easier, especially unit 3. So let's know how to draw it from here. So on, off, on, off. In the on state, we see that what? So first I'm looking at the inductor current. In the on state, we say that the inductor is conducting. The current in the inductor will rise, not from zero because we are in a steady state. A certain value, let's say A, it will rise to a certain value B in the on state. Then now when it is off, the inductor now starts supplying current because it's stored current. It will now start discharging the current. It will now start supplying current till it gets to the point A. Then when it comes on again, the inductor picks the current again. So picks the current, increases. When the switch goes off, inductor discharges, and so on and so forth, and so on and so forth. Sure. Now let's see what happens to our switch current, our transistor current, IQ. So in the on state, current going through this branch is the same current going through the switch, right? So the switch picks the waveform as the diode in the on state. So here it's at A here, same, it's at A, then it increases. Sorry, yes, it increases to a certain value B here. You get it? Then the switch goes off. The switch goes off. When the switch goes off, now no current goes through this branch. So the current in the switch goes to zero and remains at zero until the switch comes on, in which case the current through the switch is the same current through the diode. So to pick the same form as the current through the inductor. Like this. It goes off, current in the switch goes off, it comes on, it picks the current as the current through the inductor. Beautiful. Now let's see what happens to the let's see what happens to the diode current. Let's see what happens to diode current. Now, in the on state, we said in the on state, the diode is non conducting, it's reverse bias, no current current going to 0 amps. So in the on state, diode is not conducting. Now, in the off state, when the switch goes off, the inductor starts supplying current through the diode. So the diode now picks the waveform of the inductor. So it jumps up, right? And then picks the waveform of the inductor. So here too, this your B here, this your A here. You get it? So that's it. That's how the waveform come about for those who couldn't draw them. And it's important to know how to draw it. Because the question comes, sketch the waveform of the it's in a number of questions. Then switch goes off. So switch comes on. Switch comes on. So inductor is non-conducting. Switch comes on. So diode is non-conducting. Sorry. Diode is non-conducting. Switch goes off. Freewheeling occurs. Diode now starts conducting. So it's to pick the waveform of the inductor here. Pick it up. Fantastic. Brethren, the Lord is good. This is how the waveforms are. Now let's see how to calculate the average current. So I'm cleaning this off. Cleaning this off. Okay. Yeah. Um, be guided. All right. So now, so this is the inductor. This is the switch, or this is the transistor. This is the diode. All right. Now we said that what the average. So this is the I average. Okay. So if you can have this table of waveforms, average current, and RMS current. The stream has been going on for some time, but I think we will end after this. We will end after these waveforms. So we've learned the on-state losses. Next stream, we'll talk about the off-state losses, switching losses, talk about the thermal problem, and then hopefully we'll talk about the flyback converter. Okay, so with using some questions that will come in the midterm, hopefully. Optimism. So now we said that the average current is given by the area of this waveform, area that this waveform divided by the period. So here's our duty cycle, don't forget. This 1 minus d of t, right? Don't forget. So here I'm having dt here, then it's off for 1 minus d of t time. Now the area under this curve is just what? This is just a trapezium and a trapezium, right? So it's just two trapeziums coming together. So the area of a trapezium we know is half multiplying sum of parallel times perpendicular height. Right. So here under this one, the area under this is half. Let me write it here. Half multiplying sum of parallel side. That's a plus b times parallel side dt. Let me use capital letters. Plus same thing for the other side. Half a plus b. Half a plus b. So half plus half gives us 1. Half plus 1 gives us 1. So that's how come the area of this is just I'm coming. Coming. I'm coming. I'm coming. Let me see something. This was half a plus b. Height is dt, right? Plus what? Half a plus b dt. Coming in. 1 minus dt. Sure. So here is 1 minus dt all over t, right? And when you sum this, you hold on, okay? when you sum this, you get a plus b over 2. You get a plus b over 2. RMS current is given by square root of a square plus b square plus ab all over 3. Now for the diode, for the transistor, we are using the area at this side, right? So it's given by a plus b over 2 times the on state is on at dt, right? So times d. So for the transistor, this is a d factor. So I have d over 3 multiplying a squared plus b squared plus. Then for the diode, it is on for the off state rather. So multiplying 1 minus d. Here I'm having 1 minus d over 3 a squared plus b squared plus ab. Right. So this is how you find the average and RMS current of the waveforms. This is very useful in solving the questions here and in Unit 3. So we kindly pay attention to them, okay? So next time we'll see the switching laws and the offset laws. So how do we use this? How do we use this? You see, we said that for the, let's say for a MOSFET, right? It's modeled as a resistor. And we said therefore the power, the on-state loss in the MOSFET is given by R times I RMS squared. So then the RMS value of the MOSFET, which is the transistor, will be given by this. So once you have the A and B of it, you can just find the RMS value of the current. So that's how we use this table together with the first table that we drew. Thank you very much for your time. Come back to this video when you want anything to remember, and we will continue, God willing, over the weekend. All the best in your studies and have a wonderful sleep.